Alright, so here's our first problem. This is kind of just the nuts and bolts, no application. It's got a little bit of everything. I'm going to go a little bit fast to try and keep the video kind of short. So if you need to pause, rewatch, rewind, that's fine. So first, what I would do if I were you is label each of your equations. I'll use different colors, but I would still label them if I were you, especially if you're only using one color. So our first equation is a slope-intercept form. I start at the y-intercept. My slope is 1/4, so I go up 1 over 4. Be sure to continue the pattern and mark every whole number point as you can. So like 4, 3, 8, 4, all the ones that land right on the nice points, you want to mark those. And then I'm going to draw a line here. So I'm doing this just to be as accurate as possible. I'd use a ruler if I were you. It's not really necessary. If you put all the points on the integer markers, you'll be able to tell when they meet at a nice point and when they don't meet at a nice point. So our second equation is standard form. So I automatically do this. Find the intercepts. If x is 0, I just cover up the x. I have negative y equals -2. So y must be 2. If y is 0, cover up the y. And I get 2x equals -2. So x must be -1. So I'm going to go ahead and plot those. Alright, so this was equation 1. This is equation 2 here. So make that red. And that's 0, 2. So look, I've covered the same point. So I know they absolutely do meet there. -1, 0. And I'm going to continue my pattern. And then I'm going to try to draw my very straight line. Shucks, I wanted a red one. There we go, not bad. That'll do. Now let's pick another color, or again with the y-intercepts. So if x is 0, cover that up, I get 7y equals 21, y is 3. And similar method gives me x is 7. So 0, 3 is there, doesn't meet. 7, 0 is here. This slope is -3 over 7. So slope of -3 over, rise of -3, run of 7 is totally reduced. So there's no points in here that I should have colored that I didn't. So we can see that it's not going to meet at a very nice place. Sometimes it's easier to do what I just did and get carried away graphing and forget to shade. This is one of those times that you're going to be very happy that you labeled your lines, because now you can go back and say, oh, I forgot to shade under the blue line or under line number 1. But I can do that now. Is 0 less than 0 plus 2? Yes, it is, so I shade below. And then test the red line. Which one is this? I don't remember. Well, this is line number 2. I use the color code. You're using the number code. So test it. Is 0 minus 0, is that greater than 2? Greater than -2? Yes, it is. So we include the origin. In our third line, 0 plus 0, is that less than 21? Sure is. So we shade in here. So we can see this is going to be one point that is not right on the even number, so we're going to have to find that. Alright, our last line is going to be x is greater than or equal to -1. So it's in a vertical line and we're shading to the right. So, whoa. No, let's use this here. At x equals -1, and we're shading to the right. So our feasible region is within here, up to this point, that point, and here. Alright, notice we don't care about this point. Though I marked it on my graph, this point here, I do not care about it as far as for my feasible region. I'm only looking for the corners. So there's 1, 2, 3 corner points. So it's easy to see that this is negative 1, 0. That's one of my vertices. This is 0, 2. It's another one of my vertices. This is the intersection of lines 2 and 3. 2 and 1, my bad. Alright, so 2 and 1. So I need to find where they intersect. Since I have a y equals, I'm going to use the substitution method. So I have 2x minus, nope, my bad. It's equation 1 and 3. So I have 3x plus 7y equals 21. So I'm going to replace y with this equation, which gives me 7 times 1/4 x plus 2 equals 21. So I'll distribute the 7 plus, it gives me 7/4 x plus 14 equals 21. Subtract 14 from both sides. So this is where you got to listen to what I'm saying. And I'm going to get a common denominator here. So if I subtract 14 from both sides, it gives me a 7. This is the same as 12 over 3x, 12 over 4x. It's the same as 3x plus 7 over 4x. So it gives me 19 over 4x equals 7. So I multiply both sides by 4 over 19. And that gives me x equals 28 over 19, which is approximately 1.474. Y. Apparently that's the edge of my tablet. To get the y, I plug it into this. So I plug in 28 over 19 in for x here, and that gives me, solve that out, and you get approximately 2.368. So then my 3 coordinates are negative 1, 0, 0, 2, and 1.474 and 2.368. Alright, so now all we need to do is evaluate all those points in the max-min function. So I'm going to get some of this stuff out of the way. And then use our max-min function. So our 3 points are these. And I'm plugging them into this function here. So that gives us, if we plug in 0 or negative 1, 0, that gives me a negative 2 times negative 1 is 2 plus 0 equals 2. If we plug in 0, 2, we have 0 minus 3 times 2, so we get a negative 6. And then if we plug this in, we get a negative 2.948 minus 3 times this is going to be a negative number, negative 3 times that, 7.104, which gives us a negative 10.052. So because this is an unbounded region here, because we have this goes on forever, we got to investigate those extreme values. So we're going to look at, just kind of use some common sense here as we discussed in class. The numbers, any coordinates here are going to be a negative x and a negative y, right? So they'll be both negative numbers. If I plug them into this function here, so if I plug in a negative x, let's try this, a negative number, and plug in another negative number, well, a negative times a negative is going to be a positive, so I'm going to get a positive number for this part. Negative 3 times a negative number is going to give me a positive number. If I add 2 positive numbers, I'm going to get an even bigger positive number. So as these values, as we look deeper and deeper into this infinitely negative zone, we're going to get larger and larger numbers. So this function tends to positive infinity as we go towards the try to find the edge of this unbounded region. Since the max goes to infinity, of our values we need to select the minimum. So of our three values, this is the minimum. Alright, so our minimum is at our minimum is a value of this with the x and y coordinates these, and then there is no maximum.